Hello, everyone, and welcome to another Jakarta Tech Talk. My name is Serena, and with me here today, I have Thomas and Toby, who will be presenting on the topic of rapid Java startup without compromise, a deep dive. If you have any questions throughout today's presentation, feel free to ask them in the chat or use the Ask a Questions tab. Toby, Thomas, over to you.
Thanks, Serena. So my name is Tom Watson, and along with Toby, we'll be doing a deep dive into the rapid startup without compromise, in particular with cloud-native Java applications. But first, let's go a little bit about ourselves. Like I said, I'm Tom Watson. I work at IBM in Austin, Texas, mostly involved with the Open Liberty project, which is our open source project for implementing Jakarta EE and MicroProfile specifications. But I'm also involved in several other open source projects, both at the Eclipse Foundation and Apache Foundation, as well as involvement in various specification groups at the foundation. Toby?
Hi, thanks, Tom. Yeah, so my name is Tobi Ajila. I'm a JVM developer on the OpenJ9 open source JVM project. In the past, I've worked on FFI for Java. I've also worked on value types and more recently virtual threads. Currently, my main focus is on startup enhancements and so technologies like checkpoint restore, which we'll talk about today. Most of my career has been spent working on JDKs, and that's what I enjoy doing. Back to you, Tom.
Thanks, Toby. First, just some IBM legalese. Anything we talk about with regards to plans or dates are subject to change. And then just a few more notices and disclaimers. You can read those in your spare time. But let's go ahead and get into the main topic at hand. So first, we want to sort of set the stage of what are the challenges in the era of cloud native. Over the past several years now, we've seen industries and technologies move into the cloud, and many of our users and customers are in this kind of journey of moving from on-prem into a cloud native environment, either moving to hybrid cloud or fully going to public cloud. And as this shift happens, there are several challenges or demands that are being placed onto application frameworks and also the underlying JVM technologies. And so within the product that I work on, WebSphere, we noticed, even over 10 years ago that we needed to improve quite a bit in the terms of developer productivity and what we call developer delight. And that's where the Open Liberty or the Liberty project was born, was to address this need for helping developers be more productive. So the Liberty runtime was about being very flexible, easy to use, and something that you could run directly on your laptop and deploy your applications against and test them against directly there. And a lot of that work we did 10 years ago really became helpful whenever we started moving into this cloud native world, because that same kind of flexibility helped us produce a runtime that was good for developing in the cloud. So there's this concept of cloud agility where we really want to enable businesses to be innovative, focus on their own technologies, not have to do a lot of resources into their IT or their backend, and then be able to deploy quickly their cloud native applications. And as they're moving into the cloud, operational efficiency becomes important, because now that you're getting off of your own on-prem kind of hardware and into the cloud, all the resources used there start costing you money. So you really need to make sure that that's efficient. And then you need to be able to reduce the costs to rapidly deploy and achieve sustainability as you move into the cloud. So all these kind of demands sort of make us have to rethink some of the application frameworks and the Java technology underneath. So as we start moving into cloud native, oftentimes organizations start adopting DevOps for their development. And so I'm not going to go into all of these different boxes or the dev lifecycle, but I do want to just point out some of the things that we focus in on with Open Liberty in order to make the DevOps lifecycle efficient for the developer. And first and foremost, we want to be developer friendly. We want to provide that developer delight. And one of the things with Liberty is we provide something that's called just enough runtime. So if your application only needs JAX-RS and CDI from Jakarta, then you can just enable those technologies, and then the runtime will only load those up. And that can help save on startup time, memory, and disk footprint, because we can package up just the runtime that you need for your application. We also have integration with the popular IDEs as far as tooling goes, that for targeting the Liberty runtime in Jakarta and MicroProfile in general. So we have plugins for IntelliJ, VS Code, as well as Eclipse. And then we have something called a dev mode in Liberty, which allows for fast interloop development, where you can just focus on your code in your IDE. You can code, save, and then everything underneath gets taken care of as far as deploying to your local running environment with Liberty. Or it can also do interloop development within a container, running in a container. And as I mentioned, Liberty itself implements the Jakarta EE specification, as well as the old Java EE specifications and MicroProfile. And then we also have support for Spring-based applications, either just directly using the Spring framework in your typical web application, or Spring Boot applications as well. And then as far as it goes to deployment and agility in the cloud, Liberty provides operators that can facilitate the Kubernetes types configurations and the more complicated DevOps tasks whenever you're deploying and running out in the cloud. Liberty itself is designed for continuous integration. We ourselves develop the project with continuous integration, and we have monthly releases. And we really want to enable the developer to be able to quickly upgrade from one release to the next. And the way we achieve this is through something called zero migration, where we don't expect you to be able to have to change your application code or even the configuration associated with it when you're moving from one release to the next. So if you're using our container images, you can just use the latest one, and each time you rebuild your application, you can pick up the latest enhancements, the latest bug fixes, and perhaps even security fixes with ease, without having to worry about it breaking your application from one release to the next. So for this particular talk, we're really going to focus in on the running out in the cloud, and what it means to be operationally efficient. So with Liberty, we have tight integration with the Semeru runtime and the OpenJ9 technology underneath. Whenever we're running out in the cloud, or not even in the cloud, we can provide a better throughput with Java, and we do that through a number of ways. Through utilizing the JIT compiler, we have something called the Semeru Cloud compiler, and all these things really can lend to having better throughput. Also, the Semeru runtime is very memory efficient, so we can have a lower memory footprint as well. And all these things kind of lend to being able to have fewer instances of your application in order to service the peak demands that come into your application. And this all becomes important because in the cloud, all your cost structure is around how much CPU you use and how much memory you're using in order to keep your applications up and running. So over the years, whenever we're moving into Java Cloud, there's been this kind of focus on fast startup. But why is fast startup important? And it really comes down to this concept of scale to zero. So in Kubernetes, there's various autoscalers. Knative is one example, which is what this picture is kind of showing, the Knative runtime. But the basic idea is that as your applications stop having traffic into them, and maybe there's some quiet periods, perhaps in the middle of the night or other times of the day where your particular service or application doesn't need to have any requests coming to it. And at these periods of time, you really want to reduce your instances down to as few as possible, and ideally down to 0, because then you're using no CPU, no memory, and you can reduce your overall costs during that period of time. But whenever requests start coming in and you start getting demand coming in, you need to be able to rapidly ramp up your instances of your application in order to meet that demand. And in order to have low latency or a good user experience as those instances are coming online, you need your application to start up very fast. Ideally, less than a second, but really you want it below sort of 500 milliseconds or so. And then that really enables you to scale up very quickly and be able to have a good user experience. So over the years, there have been a few different approaches to making very fast Java startup. One of them is using native compilation, so using something like the Graal VM native compiler, and that has proven to really be able to have applications start very, very fast, well under 100 milliseconds. We can see startup time for Java-based applications. But you do have to live with some compromises when you natively compile. There's some of your libraries you're using may not work well within whenever they're natively compiled. It's a closed world environment, so some things are a little bit more difficult, like reflection. You need a bit more tooling and configuration to make sure that all works. And then whenever you're actually running, all the Java APIs may not work the same way they do when you do the full JVM. So with Liberty and Liberty InstantOn, we've taken a different approach. We have a holistic solution that provides fast startup without compromise. So that compromise is we want to be able to have startup times that approach native startup times, but without compromising all the functionality that we've gotten used to over the past 25 years or so with the Java runtime. And so the way we do this is through a technology called checkpoint and restore. So there's an open source project called CRIU, which is a Linux technology. This particular solution is Linux only. And what CRIU enables you to do is to take a checkpoint of an individual process, and that captures all the state of the process such that at a later time, CRIU can restore that process and get it up and running exactly at the point that it was checkpointed. And that restoration is very quick. It can bring this up in a matter of milliseconds, well under 100 milliseconds, to get you back up to the state of running that particular process. And so the approach we're taking is to basically find the point in time in the startup process that we can freeze your application such that it'll be safely in a state that can be safely restored into multiple instances when we're trying to ramp up your application in the cloud. And so we're the Liberty team, along with the OpenJ9 and CRIU runtimes, we're working very closely on this solution. So there's things we do in Liberty to prepare the runtime for the checkpoint, but then also the JVM underneath, the CRIU runtime, also has a number of things that it does to prepare for that checkpoint, and then also to restore and resume that application whenever we're restore it. And the key thing that we focus on is doing container support. We view this InstantOn as something that you do when you're building your container, so that when your container image for your application, so whenever you start up that container image, it just immediately starts up very rapidly to bring up your application instance. So with that, I'll let Tobi go into the details of Serverless InstantOn.
Yeah, thanks, Tom. So first I'll start by just briefly describing the tech stack you can see on the right. So at the bottom is the container image, as Tom was talking about. In this diagram, it's basically an encapsulation of the OS and the CRU utilities packaged as a container image. The solution we're describing today, the InstantOn solution, is a container solution. So it's intended to be deployed on container engines like EKS, AKS, OCP, that sort of thing. The solution bundles everything you need. So CRU being the main one, but also the required capabilities on the binaries and things like that. So CRIU, as Tom introduced earlier, it stands for Checkpoint Restore in User Space. So it's a project that began officially in 2012. It started a bit earlier when they were still doing experimentation in the kernel space. But it's essentially a utility that can take a running container or individual process, checkpoint its states. It does this by using things like ptrace, netlink to acquire the state of the process at the given time, and then it suspends it, serializes everything to disk. So things like all the OS resources, all the file handles you had opened, shared memory, register information, and then on restore, it maps. It basically reruns all the system calls that are used to create the initial state, maps back in all the memory, the register values, etc., and then resumes. So CRU has a command line interface that you can use to take a checkpoint restore, and also has a native API. And the main way we interact with the CRU is with the native MPI via the JDK, but on restore we use the CLI via the Liberty startup scripts. So above that is Serverless InstantOn. Serverless is IBM's commercial JDK offering based on the OpenJ9 JVM. OpenJ9 is an open source JDK. It's been around for a while. It was open sourced in 2017, but it was based on the pre-existing closed source JDK that's been around since the early 2000s. It's a JVM that has good performance characteristics in cloud environments, so things like low footprints, fairly quick startup time out of the box. So it's very conducive to cloud environments. OpenJ9 offers something called CRIU Support, which is a way for users to leverage CRU capabilities. So it includes an API that offers access to Linux CRU functionalities. But it's more than just an API. It also has compensations, and we'll go into that in more detail later. But these are things that the JVM does to make the checkpoint and restore more seamless. And so that's an important part of the solution. It also provides tracing and logging support on restore images, so serviceability support, just to make debugging experience simpler. So InstantOn, Serverless InstantOn, is the branded name for the OpenJ9 series technology, and Liberty InstantOn builds on top of this. Next slide, please. Okay, so here is the CRU Support API. It's fairly simple. It uses a build-a pattern to create the instance. At the top, with the third and fourth methods there are APIs just to query the whether CRU is supported on the machine. So the second one returns true if CRU is supported on the machine, and if you've provided the correct command line arguments to enable it. The one above it is checkpoint allowed is a superset of the one below. It does the same calls, except that it also queries whether you are allowed to take a checkpoint at the given time. For performance reasons, we by default only permit a single checkpoint, so that on the first restore, the JVM knows that it will never be checkpointed again, and then is free to generate compiled code that is specific to that target machine. Without that, we have to be safe and only generate portable code, which does come at a performance cost. The register post checkpoint, post restore hook, and pre-checkpoint hook calls are ways for users to run code right before checkpoints and right after restore to do things like fix up state. And the register restore environment file is a way to add new environment variables on restore. The calls below that are ways to control how the checkpoint is taken. For the most part, they mirror a lot of the CRU natives. Things like setting logging, whether to leave it running, where to store the image files, etc. Next slide, please. Okay, so here we're going to look at the workflow for checkpoint restore and what we're trying to achieve. So in a typical deployment, you would build and compile your app during the build phase. So this is offline. And then when you deploy it, you would start your application. And I have it in different colors because when you start an application, there's a certain amount of time required to start the JVM. These things like loading the JVM libraries, doing initialization, and then loading the core JCL, initializing those classes. And once the JVM is initialized, then you start the application. And so that also involves loading classes and initializing them. And after that, the application is ready to run. This doesn't happen instantaneously. It does take time. So here's a visual representation. It's not to scale, but it just shows you that things don't start instantly. It does take some time before you hit steady state. And so that's the amount of time that's latency that you may incur if you're doing a scale to zero solution, for example. Next slide, please. So with InstantOn, the goal is that we want to move as much of that app starting phase into the build phase as possible. So we want to take all that initialization, do it at build time, such that when we deploy, we have a much faster path to steady state. Next slide, please. So essentially the way you do this is you start your application in the build phase, and then at the point where it's ready, but before you've made any external connections, that would be when you take your checkpoint. And so essentially you'd freeze the application, serialize it to disk, and then you save that into your container image. Next slide. And then once you do that, you can just resume it at deployment time. So resuming an application doesn't happen instantly. It does take a bit of time, but as you can kind of see in this diagram, the amount of time it takes to restore an application is far less than the amount of time it takes to start the application. Typically, we see a 10x improvement. Sometimes it's even larger, up to 15x. So these are the kinds of performance gains, startup gains that you can experience with InstantOn. Next slide, please. So the way a checkpoint is initiated, we do a self checkpoint. That is that the application itself triggers when the checkpoint happens. So using the API, the application will call checkpoint JVM, and then the JVM will run hooks just to ensure that the state is sane for restore, and then it will trigger the CRU checkpoint using the native, and then it gets written down that way. There are some other approaches that use async signals to do a checkpoint. We've done some experimentation, but we still feel like this is the best mode for checkpoint, as it's a much more controlled way to checkpoint the JVM, ensuring that the state is resumable upon restore. Next slide. Okay, so CRIU is a very powerful tool, and you'll see in demos later how it can greatly improve startup time. However, with CRIU, you can take a running process, checkpoint it, restore it at a later time, or even on a different machine, which is great because this enables us to get the startup gains that we're looking for. But there are also some consequences associated with doing that. The environment in which the checkpoint is taken may not match the environment in which the JVM is restored in. For example, if you take a checkpoint at 10 a.m. and then restore it at 11 a.m., there may be some Java time objects on the Java heap that still hold those initial time values. And if there are certain algorithms in your application that are sensitive to those changes, then there may be issues there. Timers, for example, are things that behave in this manner. Java util timers, that is. And so those are some of the challenges just by restoring at a different time. There are other challenges that occur when you restore on a different machine. Things like available memory or the number of CPUs may be baked into the application logic. And these may have adverse effects if they change when you restore. A lot of times people will set the size, the number of threads in the thread pool to be equivalent to the number of CPUs you have. And so if you take a checkpoint on a machine with 8 CPUs and restore on a machine with 2, then you could have some performance degradation at restore time. There are also networking challenges related to restoring on a different machine. Anything that caches the host name or DNS resolution may not function properly if it changes on the restore environment. So this is why it's important to have JVM support when taking a checkpoint. In theory, you could do all of this without any support and just use the CRIU capabilities to checkpoint and then restore it, but you would run into all these problems that I've just described. So the JVM is best positioned to compensate for any environment differences between checkpoint and restore, and by doing so, it can make the restore behave in the manner that it was intended. Without the support, you would essentially have to fix up a lot of things, or your application would not work at all. And so the JVM kind of at the lower level is best positioned to do those things automatically. Now, in the previous, next slide, please. Yeah, so in the previous slide, we were looking at things that change in the environment. Here, we're looking at things that don't change in the JVM. There are certain algorithms that rely on randomness or uniqueness to function properly. These are often related to security. Examples are secure random with a seed value in it. So if you create a checkpoint, save the image, and restore it multiple times, without any compensation, the seed is going to be the same each time. And this can introduce a security flaw. So it's important to provide a certain amount of uniqueness when storing the JVM. There are other cases where there's certain security states baked into the JVM, maybe secrets and strings, things like that. And you don't want those things to persist in the image. So in these cases as well, it's important that you are able to clear all that sensitive information before the checkpoint is taken, and then rebuild it if needed upon restore. So these are some of the things that the JVM can do as well. Next slide, please. So for the problems that I've just described, it identifies a need for the JVM to compensate between the differences between the checkpoint environment and the restore environment, whereby the goal is to enable the restore program to behave in the new environment as if it was started there originally. So essentially, you need a way to bridge between the checkpoint and restore environment. And so this is what I've been calling compensations. And to achieve this, there's one main requirement, and you essentially need a way to patch the state just before checkpoint and after restore. And the way we do this is with hooks, and we saw an example of this in the CRIU API. But these hooks run just before we take a checkpoint and just after. The JVM has its own hooks as well that are there, and users can also add hooks as well. Ideally, the JVM can handle everything, but there might be things in the application itself that we have no way of knowing about, and so it's important that the user also has the tools to do this on their own. If you're using this technology with a framework, the framework itself, like Liberty, also installs hooks and ensures that there's a smooth transition between checkpoint and restore. So it does make it a lot easier for the end user using a framework. Next slide, please. Yeah, so again, this is just showing how users can do this. We've recently extended this API such that you can request whether these things run in single thread mode or in multi-thread mode, and also associate a priority with these hooks. By default, the ones you see, they run in single thread mode, and that's just because if you're making global state changes, you need a way to do this safely without race conditions. So in the next slide, we'll take a look at how that works. So next slide, please. So the way it works is before a checkpoint is initiated, there may be many application threads running concurrently. When the checkpoint is initiated, we will wait for these threads to hit a safe point, and then we'll halt them. And then at that point, there's only one application thread running, and that thread is going to be the checkpoint thread. This is also going to be the thread responsible for running all the single thread hooks. And so this could be, and some of the things we do at this stage is do a heap walk to scan all the instances that we might need to modify. And then once we run the hooks, then we're ready to run a checkpoint. Next slide, please. So on restore, when the JVM is restored, we're still in that single thread phase. So there's still only one application thread, and this allows us to do updates using new information from the restore environment, and we're able to do global updates without incurring race conditions. And so once all the single thread restore hooks are run, then we re-enable all the application threads. And then the application resumes. Next slide, please. So where to take a checkpoint is probably the most difficult choice to make when using CRIU support. The later the checkpoint is taken, the better the start performance will be, because you're shifting more computation to build time. However, it introduces more complexities because as you have more application states being run at build time, you potentially have more things to fix up at restore time. So there is a bit of a trade-off. The faster you want your checkpoint, the more code you have to run at build time, and potentially the more fix-ups, so the more complexity that you incur. In our experience, we find that if you're using something like Liberty, it's actually a lot easier, because Liberty gives you two choices as to where to take the checkpoint. And so it's a much simpler for the end user. You pick from the available choices. If you were to do this directly on Samaru, you'd have to determine where to make the call to trigger a checkpoint. Next slide, please. So there are some concerns that you have to be aware of when using this feature, and I've alluded to them earlier. But one of the main ones is portability. The JVM has dynamic compiler, JIT compiler, that generates code at runtime. And so it compiles and optimizes the bytecodes to get optimal performance for the target machine. So it often takes into account machine capabilities like the type of CPU you have, whether it's Broadwell or Skylake, the exact CPU version, the kind of vector instructions available, things like that. So there's a possibility that the JVM might be checkpointed on a machine that has different capabilities than the machine that it's going to be restored on. So for this reason, at checkpoint time, we're always conservative with the optimizations that are performed, and we always ensure that these are portable. By default, we assume that the JVM will only be restored once. So as soon as the JVM is restored, then we are free to make optimizations that target the machine that it's restored on. However, if you want to do multiple checkpoints, then you have to disable this. And so the first option, that's the non-portable restore. If you do a minus for that, then you disable this feature and you're free to take as many checkpoints as you like. However, there is we will be more conservative in the code that's generated. Now, there's also portability concerns at the OS level. There are some platform-specific library implementations, and so when you load libraries, you may load the libraries internally themselves check to see what kind of CPU you're on, and they link to specific to processor-specific implementations of those library APIs. And so when you link those libraries at checkpoint time, you may have frames in your process that have processor-specific implementations. So we use glibc tunables to disable this feature, such that we only link with portable versions of libraries, and that ensures that you're able to restore the JVM on as many different platforms as possible. Next slide, please. When using a feature like CRIU Support, because you're baking in a live JVM into your image, this might cause challenges in the area of serviceability and tuning. It can be burdensome to have to rebuild your image every time you want to add diagnostic options. And if you want to tune your application for a specific target, you don't want to have to make a specialized version of the image for each target. So CRIU Support offers the ability to add JVM options upon restore. We currently don't support every option. There's certain things we support, and here's an example on the right. It's like method tracing, JIT control, verbose logging, diagnostic dumps, GC thread counts. But the list is growing. We keep adding new things that you can do on restore. One of the things we're working on is heap resizing right now. So this will allow you to take a single image, but resize it for the size of your container. So if you need to reduce the image from a 1 gig to a 512 megabyte image, you can do that dynamically as well. Yeah, so this time I'll pass it back to Tom. Tom, we can't hear you.
All right. Can you hear me now? Yeah. All right. So now I would go into basically the layer on top of the Semeru runtime that Tobi was describing with Open Liberty. So Tobi had mentioned where to checkpoint and mentioned that in Liberty, we basically provide 2 spots in the startup process to checkpoint. And those 2 spots are called before app start and after app start. So in the Liberty startup sequence, the JVM comes up, and then what we call the kernel is loaded, and then that is responsible for reading either your configuration, figuring out what features of Liberty need to be loaded into the runtime, and then we start processing the actual application, reading annotations, other metadata associated with the application, basically getting the runtime ready to start your application. And if you use the before app start, we'll basically take a checkpoint before we run any code out of the actual application itself. And some of the reasons you might use this as opposed to the after app start is if you have some early startup code that isn't quite ready to live in this checkpoint world. Maybe it's trying to access some remote resources, needs some credentials in order to do certain operations. And these are kind of things that you don't want to build into your container image. So if you have applications that need to kind of do this kind of stuff right when they're starting, then you may have to resort to using the before app start. But if your application doesn't do any of these kind of things, like starting a transaction or accessing that remote resource with some kind of credentials, then you can start using the after app start. And so this is a later point in the startup sequence. And so if you can use this, then your restore time is obviously going to be a bit faster because we don't have to rerun that start sequence of your application. And then once we restore from that point, all Liberty does at that point is open up the ports and start being able to take incoming requests in that environment that you're restoring the actual application. So here we'll go into a short demo. So out in the Open Liberty project, we have this sample getting started. So this is a real simple application. It just uses XML Jakarta RESTful services, as well as MicroProfile health and some of the other MicroProfile specifications. But I won't focus so much on the actual application. What I really want to focus on is how we containerize this application. So for this particular application, we'll just be using a Docker file. It's being based upon what we call our kernel slim image. So this only contains the smallest bit of Liberty, and then that's the thing that can load up the features that you have specified in your configuration. So you can copy in your config. This is what tells the Liberty runtime what features to load and various other configurations for your application. And then this step here where it runs the features script is basically just loading up those features into that container image so that we only package into the container the individual features that you actually need, so we can make your application image small as possible. And then the final step is just copying in the various resources and the actual application. In this particular case, it's a WAR file into the apps folder of the container. And this final step is a configure script. So this is optimizing your container for Liberty. This isn't actually doing anything with InstantOn. It's just establishing some caches. I'll go into that in a bit whenever I'm building this. So let's go ahead and build this application. So I'm just going to build the original application with no InstantOn. So it's going to go through this, and the longest part is going to be running that configure script. So I mentioned this in the Docker file, but just a little bit more details on what this is doing. It's establishing various caches, both at the Eclipse J9 level in the form of a shared classes cache. So it's priming that all with both the Liberty runtime as well as the application code, and so the shared classes cache can store a bunch of data associated with the classes, so that it can be loaded that much faster the next time you start the actual application. So once that's all finished, we can commit that particular image, and now we have the base image with the application. So I'm going to go ahead and run this image just to show you the original startup time without InstantOn. So usually it comes up just around 5 seconds. Here is 4.7. So this is the actual application itself. It has a simple endpoint for getting the system properties, and then has the various MP health, some config, and the various metrics. So it's just a simple application to highlight the runtime and the MicroProfile and RESTful services and so on. let me go ahead and shut this down. Then I'm going to show you the Docker file for doing InstantOn. So it's going to look identical to the previous one. From this point, all I did is add one line at the end that will do the checkpoint. And here I'm using the after app start option for this particular app, because this application is pretty simple. It doesn't do anything out of the ordinary during application startup. And so I'll go ahead and build this. So this is just going to reuse all the caches from the previous build of the image, up to the actual configure script. And now it's running the checkpoint after app start. Here it's bringing up the application again and getting it to the point where the application has started. And then at that point, we request the JVM to do the checkpoint. That goes ahead and saves that process image down into a layer of your container image. And then finally, we got our application, which is the getting started InstantOn image. So if I run this, you'll notice it come up much faster. So it came up in just under 300 milliseconds. So, much faster than about 5 seconds. And like Toby said, generally see 10x or more improvement, and this was definitely more than 10x improvement to get to the running state. So now our application's back and running, and everything's up and running just fine. The other thing I wanted to show was being able to do some things like Toby mentioned for serviceability. I have a run debug. So here we're passing another environment variable for restore options, and we'll just trace the sleep method. And so this is the only difference. I'm just adding this one particular environment variable so that we can enable some xtrace. So this will take a bit longer, of course, to start up because we're doing this xtrace stuff. But you'll notice that anytime we get that call to the sleep, it'll print out the information for that particular call. So it kind of shows that you can take that checkpointed process and now change some of the JVM settings in order to get some debug information perhaps that you need to get out of that application. But the main thing I wanted to point out here is that we didn't need to change the application. We could take even just that original application image, and we just have to put on top of that one more layer that does the checkpoint, that goes ahead and does the Semaru checkpoint JVM and gets everything saved into a safe state, and then we can restore that application image over and over. So I can run this multiple times, getting it running concurrent instances out in the public cloud, for example, in order to ramp up very quickly from like a scale to 0 type scenario. Let me go back to the talk here. Okay, so for those that maybe are already familiar with checkpoint and restore technologies and pay attention to like the OpenJDK project, there is a project related to checkpoint restore called CRIU. And so this is an OpenJDK project that is also looking into these types of solutions of using checkpoint and restore for rapid startup time of your applications. And there is a project related to this called org.cric, which is a library that kind of sits on top of a crack-enabled JVM. But what it allows for you to do is depend on this org.crack API for your own applications. But then when you're running on, say, like a hotspot JVM or another JVM that doesn't necessarily have JDK crack support, that just acts as a shim so that your application can continue to run. It obviously won't get any calls to it, but it allows for you to make a dependency on it. And why this is important is it allows for applications that want to participate in checkpoint restore to add their own hooks. In this particular case, they call it a resource in CRIC. So you can register a resource, and that resource will get called before checkpoint. So it's similar in nature to some of the hooks that Toby had mentioned. That's provided by this org CRIC library. And basically, these APIs allow for your application to participate in this checkpoint store. So at the application layer, you can also do similar things that you may need to do in order to prepare for a checkpoint, and then also fix things up on the restore. And the reason this is important, or the reason that we're looking at this with Liberty InstantOn, is that the Spring framework and Spring Boot are looking also to utilize checkpoint and restore to make Spring Boot-based applications start up rapidly as well. So the upcoming Spring Framework 6.1 is adding integration to org.cric so that it can do compensations during the checkpoint as well as the restore. And the way they do this is they have a resource that they register that is basically the Spring lifecycle processor. So the Spring lifecycle contract hooks into this checkpoint restore. So during a prepare, it stops all the Spring managed lifecycle beans. So any lifecycle beans that are either defined within the Spring Boot runtime itself, or your application will get stopped. And then on a restore, it restarts the Spring managed lifecycle beans. So typically in the past, you would see these things just start up and then shut down, and then the JVM would exit. With Spring Framework 6.1, we can start considering where it will start, stop, multiple times possibly within the life of the application. And now with Liberty InstantOn, with our 23.00.10 beta that came out over a month ago, we also now offer an implementation of org.cric that sits on top of Liberty InstantOn and the Cimeru InstantOn CRIU support underneath. And so this allows for us to deploy Spring Boot applications to Liberty that also can have a rapid startup time similar to what I was showing with a Jakarta and MicroProfile based application. So let me just do a quick demo of that, and then hopefully have some times for questions if there are any. So here I'm just using a Spring Boot example from Open Liberty. So this is a very simple application that I won't go into for this demo, but for the Docker file, it's similar. All I added to the example is to do this checkpoint after app start. So let me go ahead and build this. So it's going to go ahead, and I'd already built the original image, so the configure script already ran, but now I'm just doing the checkpoint. And you'll notice that this is bringing up Liberty again. It's bringing up the Spring runtime. Here I'm using Spring Boot 3.2 M1. That's where they first started adding, the integration with CRIC. And then what we'll notice, if you can read this, is the default lifecycle processor is going to stop the lifecycle. Actually, get down to the bottom here. It's going to stop all the Spring lifecycle beans and get it prepared for doing the checkpoint. And then we actually, perform that checkpoint, and everything's saved into our container image. And now we can run this actual application, and this will, here it came up in 369 milliseconds. The original one I could show you, but it basically comes up in right around 6 or 7 seconds. So, a drastic reduction of the startup time for your particular Spring Boot application here. The thing you'll notice whenever it's starting is here again, the lifecycle processor is restarting the various beans that are included, the lifecycle beans that are included in this application in order to get it restored and back up and running. Okay, so that's the end of the demos, and really the end of the talk. We can just go into the summary. So in summary, just adapting and thriving in the cloud world requires you to evolve, your not only development, deployment, but also, as we showed, the runtime for the cloud native world. So with the Semaru runtime and Liberty, it's a versatile runtime for these purposes, and you can really utilize the cloud resources efficiently. And we believe InstantOn is a key capability that makes Liberty and Semaru an even better runtime for these kind of serverless type use cases. So with that, I just want to say thanks for attending, and I don't know if there's any questions to be had.
For such a great presentation and all the wonderful demos. I'll go into the Ask the Questions tab. Let's see if there's anything in there. No. Oh, we'll give them a couple of minutes here to drop down any questions. But in the interim, I just, again, wanted to say thank you very much. And also that we are looking to book. We are already talking about 2024. I know it's crazy. But we are looking to book some more Jakarta Tech Talks in 2024. So I will post the link in the chat. And if you are interested in sharing some information with your peers, please feel free to fill out this form and we can get some time scheduled in for you. So let's just take another last look. No, just a nice thank you from Neil. Thank you, Thomas and Toby. Great talk and demo. That's great. Well, thank you both so much for your time today and have a wonderful rest of your day.
Thanks.
Take care. Bye, everyone.